Hi, my name is Ahmad Najmuddin bin Zamri. My metric number is CD190327. I'm from Team 1A. We present you about Lab 1 cantilever beam experiment. Okay, for the first lab, we talk about theory. First, cantilever beam, a stiff structural element that is support at one end and free at another is known as a cantilever beam. The support must be fixed to ensure that the structure is static, which implies that it can sustain force and moment in all directions. Okay, next one is beam. A beam is a structure element that resists load that are applied literally to the axis of the beam. At primary mode of deflection is bending. Reaction force are generated at the beam support points as the result of the load applied to it. Okay, the next slide is about result for the specimen brass aluminium mile. Then we talk about observation. This experiment is conducted with varied load applied and different specimens such as brass, aluminium, and mild steel. To compare different types of specimen can change beam deflection, which can affect the elasticity experiment. The load was increased from 5 to 30 kN. The experiment findings include the statistic on increase and decrease for all three types of material. Conclude from this experiment that mild steel has the lowest deflection and aluminium has the highest. Okay, for the next slide is the calculation formula. We use 1 over 2 bn power of 3 and y equal to L power of 3 over EL times with W over 384 plus W minus B W2 over 192. Okay, the next slide is about theoretical value for brass, aluminium, and mild steel. Next slide is for a graph for load versus experimental and brass. Next one is aluminium and mild steel. For the conclusion, to summarize, the goal of this project was to investigate the variation in deflection of a simply support beam with load and different beam materials. This experiment showed that the beam deflect is depend on load, material, and type. Hence, material selection is critical since it affects the beam. We also learned from this experiment that aside from the specimen mild steel has the least deflection and that aluminium has the most deflection among the specimen. Okay, the next slide, this is the reference we use to do this lab report. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera to Encik Muhammad Faizal. My name is Arisha Kanti Azman. Metric number is 3190070 and I am going to present lab topic 2, which is buckling of strut. Theory. In structural engineering, buckling is the abrupt change in shape of a structural component under load, such as bending of a column under compression or the wrinkling of a plate under shear. If a structure is subjected to a gradually growing load, when the load reaches a critical level, a member may suddenly change shape and the structure and component is said to have buckled. So, Euler's critical load and Johnson parabolic formula are used to determine the buckling stress in slender column. So, the Euler's equation is pi square E times I over L square, where E is equal to 69 times 10 power of 9 Newton meter square. I is area of moment of inertia and L is the original length of the column. So this is the result for experiment 1, pin. As you can see in the table, length in millimeter, buckling load in Newton, buckling I over L square in millimeter square. So we use length 320, 370, 420, 470, and 420. So the experiment load is 108, 70, 44, 29, and 26. So we got I over L square is 9.77, 7.3, 5.67, 5.53, and 3.70. So this is for experiment 2. Result for experiment 2, pin fixed with length 300, 250, 400, 450, and 500. The load used in Newton for experiment is 171, 135, 101, 86, and 56. So we got I over L square meter square. Meter square is 11.11, 8.16, 6.33, 4.84, and 4.0. So this is our result for experiment 3, which is fixed. So the length is 280, 330, 380, 430, and 480. So the load used in this experiment are 312 Newton, 263, 212, 177, and 140. So we got the I over L square meter square is 12.76, 9.18, 6.93, 5.41, and 4.34. So the observation, based on the result from pin N, pin fixed, and fixed N experiment, the result for all experiment, both theoretical and experimental, and the value for I over L square decreases when the length of the strap increase. So from the result, we can also see that the result for buckling load, both theory and experiment, as well as the I over L square for fixed N, is the highest, and pin N experiment has the lowest value. So for calculation table 1, pin N, we use formula pi square E times I over L square. So we got E equal to 69 times 10 power of 9 Newton meter. B is 0.02 meter. D is equal to 2 times 10 power negative 3 meter. And the formula is I equal B times B cube over 12. So we got 13.33 times 10 power negative 12 meter. So we calculate for strap length 320 millimeter. So we got 88.67. So we apply the same equation and continue calculate for other 370, 420, 470, and 520 millimeter, and we can get 66.21, 51.46, 41.09, and 33.57. So for table 2, the calculation for table 2, which is pin fixed, we use 2 pi square E times I over L squared. So we use the same data as the table for table 1, but we times 2. So we get the answer for strap length 300 millimeter is 201.78. So we apply the same equation and continue to calculate for 250, 400, 450, and 500 millimeters. So we got 148.21, 113.47, 89.66, and 72.62. So for table 3, for fixed N, we use formula 4 pi square E times I over L square. So we use the same data as the previous table calculation. So we get 88.67 for straight line 280. So we apply the same equation and continue calculate for 230, 280, 430, and 480 millimeter. Here shown here is a graph for pin, which is I over L square versus buckling load. So we plot for both experimental and theoretical, and we also calculate gradient for both experimental and theoretical. Here is the graph for pin fixed experiment. We also plotted for both experimental and theoretical, and calculate the gradient for both experimental and theoretical. Here is a graph for fixed experiment. We also plot for both experimental and theoretical, and we also calculate the gradient for both experimental and theoretical. So based on the graph plotted, we can see that nearly all line plotted is linearly increased. So this proves that the relationship between the buckling load and I over L square is linear, and the buckling load is directly proportional to I over L square. So therefore, this proves that the Euler formula does predict the buckling load. So for pin graph, the gradient for buckling load experiment is 15.38, and for the theory is 9.07. So for pin fixed graph, the gradient for experiment is 13.78, and for the theoretical is 18.09. While for fixed graph, the experiment gradient is 36.30, while for the theoretical is 18.37. So the table shows the comparison of experimental and theoretical ratios by the end condition. So based from the comparison table, we can see that we can state that both experimental ratios and theoretical ratios are not consistent. So however, the theoretical ratios are more consistent than the experimental ratios. So this inconsistency occur probably due to some error that we face during conducting experiment. So question, the relationship between strut length and collapse load, and the relationship between various and fixing conditions and collapse load. So from the result, we can see that all buckling load for the experiment and theoretical for all three end conditions decrease when the length increase. This shows that the length is inversely proportional to the buckling load. So the longer the strut length, the lower the collapse load that can be applied to the strut. So besides, from the observation also, we can see that the value for the buckling load fixed is the highest, while for the pin experiment is the lowest. So it shows that the strut at the fixed condition, fixed end, can be applied with the highest collapse load. Next question is the importance of understanding the collapse load of framework, for instance, in a building structure. So the importance of understanding the collapse load of framework, such as in building structure, is to prevent a structure from collapsing or fail due to the impact of unexpected loads, or can be called as buckling. So buckling is the failure mode of a structural member that experiencing high compressive stress that will lead to a sudden sideways deflection or deformation. So for example, in a building structure, some buildings will fail progressively due to design codes of the structure that were not firm and strong enough when going through the action of an unexpected load. So therefore, the understanding the concept of collapse load of framework is very important for a design engineer to minimize the consequences of building progressive collapse after an event of column removal scenario. So this concept is highly significant in the prevention of progressive collapse or buckle for a building structure. However, purpose of this knowledge is not only to deliver structures that are safe under unexpected loads, but it is also to provide an excellent performance under everyday loads with reasonable economic costs. In conclusion, from all three conditions, we conclude that fixed condition column support is the strongest, while the least strongest is the pin condition. Fixed support column can bear more load than other condition, and buckling condition will not easily occur in a structure. Then the buckling load also affected by the length of the strut, which the longer the length of the strut, the lower the buckling load that can be handled by a support column, and the error that may occur while conducting the experiment can be prevented by ensuring that all screw handle and all experiment apparatus was set clearly and properly to avoid inaccurate reading. Reading can be taken more than once to get a more accurate reading. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and hi. My name is Muhammad Fadli bin Zulkifli and I am from Group A. Today I want to present about topic 3 that is bending of beam. Okay, I go to my first slide that is theory. A beam is a structure element that is capable of withstanding load primarily by resisting bending. When a beam is subject to a loading system or by a force couple acting on a plane passing through the axis, then the beam deforms. Shear stress parallel to the lateral loading plus complementary shear stress on planes perpendicular to the load direction. Direct compressive stress in the upper region of the beam and direct tensile stress in the lower region of the beam. Now I will go to the objective. The main objective of this experiment is to investigate the relationship between load, span, height, and deflection of a beam placed on two bearers affected by a concentrated load. In observation, first and second experiment is conducted using test specimen with dimension of 6 times 25 mm, while third experiment is by using 3 different test specimen dimension. For first experiment is to investigate the relationship between load and deflection. The second experiment is to investigate the relationship between span and deflection. Third experiment is to investigate the relationship between the height and the deflection of test specimen. And now I will go to calculation. In calculation, to get the value of inertia, we must use formula for moment of inertia. That is I equal to BH power of 3 divided by 12. To get the value of Young modulus, we must use the formula elongation equal to WL power of 3 divided by 48 times E and I. After we settle down the calculation, we can get the result from that we calculate. The first table is result of investigate the relationship between load and deflection in experiment 1. The table 2 is result of calculate from experiment 2, that is investigate the relationship between span and deflection. And the third table is the result from calculation for third experiment, that is relationship between the height and deflection of the test specimen. Okay, this is for discussion. In discussion, from the experiment 1, which is to investigate the relationship between load and deflection. From experiment 2, which is to investigate the span and the length of deflection. The increase of the deflection when the load increase. The importance to have several types of beam such as C-channel, angle bar, I-beam, and hollow section because the high number of steel compared to the solid rectangular or square section. In conclusion, that I can conclude is the link between the load, span, height, and deflection is determined throughout the experiment, and it is discovered that as the applied force grows. The deflection of the beam increase as well when the load and dimension of the test specimen remain constant. And also the relationship between span and deflection is that as and the span length grows, so does the deflection of the beam. That's all from me, and thank you.
Hello everyone, my name is Brian. I'm going to present about the experiment of deflection of curved bars and davits. First, let me see the theory for our experiments. The limiting factor in the curved bars and davits depends on the deflections when loads applies. So, theoretically, as the load increase, the deflection also increase. Using Castigliano theorems to determine the deflection and slope at various points along the length were used during the experiments. Below is the table a formula for every shape that will be used in this experiment. Next, for the observation during the experiments, there are 4 alternative structures of experiment that will be used, which is symmetrical, quarter circle, curve Davids, and angle Davids. The two digital deflection indicators are positioned at 90 degrees to each other, where these indicators will measure the horizontal and vertical deflections of the structure. The structural deflection is measured using a gauge, where this gauge is a sensitive device and must be correctly set up during the experiment. Next is the structural deflection increases both horizontally and vertically as the load increases. And finally, to compute the moment of inertia, every structure dimension is measured with vernier caliper. Here is the result, which is the graph that we plot after doing the experiments. There are 4 types of graph, which represent the symmetrical, quarter circles, curve Davids deflections, and angle Davids deflections. As we can see from the graph, as the load increases, the deflection also increases. Therefore, these two variables are directly proportional with each other. The conclusion for our experiment is, the experiment decided the connection between load, flat deflections, and vertical redirection for a crescent, a quarter circle, a bend David, and a point David. As indicated by the diagram, the greater the applied load, the greater the deflection of the structure. That's all from me. Thank you.
Hello, my name is Daniel Iskandar and I'm going to represent my team for Lab 5 thick cylinder experiment. Okay, first of all, we go for the theory. The theory of this lab is design of the pipe is SM101, so the delta length can be ignored. Assumption, the material will be stressed within the elastic limit as per Hooke's law. The material elected is homogeneous and isotropic. Plane transverse section remain constant under the action of internal pressure. And lastly, the material fiber is stressed independently without being constrained by adjacent fiber. Okay, this is the result. Radius is 20, 30, 40, 50, 60, and 70. Okay, after we cut the data, we insert to the table. We also use the theoretical straight to differentiate the answer. After that, we use the derived and theoretical stress value, and we also put in the table. For the observation, during the experiment, the respondent of the pressure gauge in the computer system need the time to respond. The hard wheels is turned to increase the pressure gauge to 3 meganewton per meter square. We must increase the value of the pressure slowly and cannot be fast when it almost 3 meganewton per meter square so that the pressure and the strain reading to be stabilized. The data is collected after press the button from the machine and the data will provide all the reading. You still have the value of the gauge reading although the hands will turn freely. Okay, now we go for sample calculation. For hook strain, we use radius 20. We insert the formula that been given from the lab report and we insert the radius and also the p-value, and then we get the answer, which is 49.7398 times 10 to the power of 6. Then we proceed to radial strain, which is we use radius 20 and we got the answer negative 49.7398 times 10 to the power of 6. And we proceed to longitudinal strain. We use the radius of 70 and we got the answer is negative 1.17. For the hook stress, the radius of 20, we use the formula and we got the answer for 3.125 times 10 to the power of 6. For the radial stress, we use also the radius 20 and we got the answer 1.031 times 10 to the power of 6. For hook stress, we use the radius also 20 and we got the answer 2.259 times 10 to the power of 6. And lastly, for the radial stress, is the radius of 20, and we got the answer for it is negative 2.0 times 10 to the power of 6. Okay, for the discussion, from the graph that been drawn, it's shown that all the hoop stress give the positive value and the radial stress will give the negative value. For the hoop stress, the radius increase, thus the value of the stress will decrease. For the radial stress, when the radius is increased, the value of the stress also increase in the negative value. Okay. Lastly, for the conclusion, there are three forms of stress, which is hoop stress, longitudinal stress, and radial stress. Human error were kept to a minimum, and the experiment was primarily focused on the program. The variation was caused by the system difficulties. The program be updated or modified in order to satisfy the requirement. That's all from me. Thank you.